In this lecture, we're going to talk about the autoionization of water, right? The fact that water spontaneously dissociates to form hydrogen ions and hydroxide ions. We'll talk about the equilibrium constant for that process, the Kw. We'll talk about pH as a way of describing the hydrogen ion concentration. And we'll talk about Ka and Kb, equilibrium constants for the dissociation of weak acids and weak bases. And we're going to talk then about the equilibrium between hydrogen ions and hydroxide ions in aqueous solution. After getting partway through this, I realized this might be a little much for one talk. So we're going to focus this one on just the Kw. We'll talk about the other three in subsequent videos. So let's make this one 16.4a. Okay? So we don't make one video too long. Okay? When we talk about the autoionization of water, what we're talking about is the spontaneous dissociation of water molecules. So what happens is in water, right, in pure water to a very small degree, right, you have water molecules in the liquid phase, right? They will dissociate to form hydrogen ions and hydroxide ions, right? And just to remind ourselves, right, here we're sort of talking about this all in the Arrhenius sense, which is, I think, the most straightforward way to talk about it. If you happen to be dealing with someone who likes to think more Bronsted-Lowry, then it would look more like this, right? You'd have water plus water, right? Because one water molecule acts as the acid, the other one acts as the base. And so then you'd get one would take a hydrogen ion from the other to make a hydronium ion, and then you'd get a hydroxide ion from the other one, right? While both treatments are valid, most of the time I will use the Arrhenius. We will talk about these in the Arrhenius sense when we're doing these problems, right? Just saves a little writing. The mathematics ends up being the same. So, right, here's our equilibrium written in the Arrhenius acid-base sense, right? It's an equilibrium, and so we can write an equilibrium constant for that, right? So if we're going to write an equilibrium constant for that, the equilibrium constant would be the concentration of hydrogen ions times the concentration of hydroxide ions in solution divided by the concentration of water, right? But remember, water here is a pure liquid, right? So as a pure liquid, one of the things we know is that what is really in these is activities, and the activity of a pure liquid or a pure solid is 1, right? And so if we put 1 in for the water, then we get an equilibrium constant that is just concentration of hydrogen ions times the concentration of hydroxide ions, right? It is just a product of the two ion concentrations. And so we give this a special name, and that is the Kw, the equilibrium constant for the dissociation of water, right? And if we look at this, right, if we do this as a quick ice table, right, if you have water as your reactant, you have hydrogen ions, you have hydroxide ions, right, concentrations, right? It's pure, so we're not worried about that, right, initially. Initially, we have no hydrogen ion, no hydroxide ion. Our change is going to be X. And at equilibrium, we're going to have, right, Don't care about that because it's going to be 1 anyway. X and X. So in pure water, the concentration of hydrogen ions is equal to the concentration of hydroxide ions because they were both made at the same time, right? And the value of that number, right? So the Kw, let's go this way, right? The Kw at 25 degrees Celsius, because the temperature does make a difference, is equal to 1.0 times 10 to the minus 14, right? And it is temperature dependent, right? Temperature does make a difference. If the temperature goes up, that number goes up a little bit, right? If the temperature goes down, that number goes down a little bit. But we tend to work most of our problems at 25 degrees. So here we're showing our equilibrium again, right? Or at least our ice table from our equilibrium for the dissociation of water, and the Kw, right? And so if we substitute in what we know, that is that the Kw is equal to the concentration of hydrogen ions at equilibrium times the concentration of hydroxide ions at equilibrium, and we now know, at least we've expressed, that each of those is X, then we can find either one because 1.0 times 10 to the minus 14th is equal to X squared. And if we take the square root of that, we get that 1.0 times 10 to the minus 7 is equal to X, which is equal to the concentration of hydrogen ions and the concentration of hydroxide ions. So in pure water, with other things removed, just pure water, the concentration of hydrogen ions and the concentration of hydroxide ions in water just sitting there is 1 times 10 to the minus 7th molar, right? And so, we've got that equilibrium, right? And we know that that is the concentration. Now, the other thing is, this is an equilibrium. And so if we disrupt one, right, if we make hydrogen ions go up, then to keep the equilibrium, hydroxide ions will have to go down, right? Similarly, if hydrogen ions go down, the concentration of hydroxide ions will have to go up to maintain our equilibrium, because hydrogen ions and hydroxide ions are locked together because of the equilibrium of water. Right? If one changes, the other one has to change to keep this number constant, right? That is the constant number. So let's consider this solution. We've got 0.0050 molar nitric acid, or 5.0 times 10 to the minus 3 molar nitric acid. So what is the concentration of hydrogen ions and the concentration of hydroxide ions in this solution? Okay, now one of the things we have to remember here is we have two processes that we have to consider, right? We have a strong acid, and so our first process is the complete dissociation of the acid, right? Then our second concern is the equilibrium between hydrogen ions and hydroxide ions. And that's always the way we consider these, right? Whenever we've got more than one process going on, consider complete processes first, right? Deal with what is complete first. Then go back and deal with the equilibrium second. So we always go complete processes first, equilibrium processes after that. All right? So complete processes we can treat like a limiting reactant problem, right? So if we go back to our nitric acid, right, is going to dissociate completely when we put it in water to hydrogen ions and nitrate ions, right, interacting with water molecules. And so if we start with an initial concentration of 0.0050 and none of that and none of that, because it is complete, right? Any complete reaction is a limiting reactant problem. And since we only have one reactant, that's what's going to be limiting. So all of that will react or dissociate, which means we know what this is. And we know what this is. Right? And so when we reach our final, right, it's not an equilibrium position, right? This is not an equilibrium reaction. We have no nitric acid left. We have 0.0050 molar hydrogen ions, and we have 0.0050 molar nitrate ions. Okay? So we deal with complete process first, get that done. Okay, so here's where we ended up on the last slide, right? All of our nitric acid had dissociated. We didn't have any of it left. We had 5 times 10 to the minus 3 molar hydrogen ions and 5 times 10 to the minus 3 molar nitrate ions, right? Now we have to deal with our equilibrium process, which is our Kw process, right? Water dissociating into hydrogen ions plus hydroxide ions, right? And so we have to look at our initial condition here, right? This is liquid, right? So we don't worry about its concentration. But here we're not dealing with 0 hydrogen ions. We're dealing with 0.0050 molar hydrogen ions, right? This number, right, that becomes our initial concentration of hydrogen ions, our result from our complete process. Now we can say we have 0 hydroxide ions because we haven't considered those yet, right? So our change is going to be, right, since we have 0 of a product, we have to dissociate some reactant. We're going to make more of that. We're going to make more of that. And when we reach equilibrium, we're going to have still liquid water. We're going to have just a teeny bit more hydrogen ions, and we're going to have some number of hydroxide ions. So if you substitute those numbers into the Kw expression, right, this is your Kw, right, you get that expression. If you solve that, even if you go through the quadratic, right, you get x is equal to 2.0 times 10 to the minus 12 molar, right? So that's really small. That's essentially not going to change the concentration of hydrogen ions. So the concentration of hydrogen ions will be the 5.0 times 10 to the minus 3 that we started. But the concentration of hydroxide ions then would be the 2.0 times 10 to the minus 12 molar. So let's consider a similar problem that is a dissociation of a strong base in solution, right? So what we said earlier, right? Deal with your complete processes first, right? And the only complete process we have to worry about here is the dissociation of our sodium hydroxide, right? So sodium hydroxide, when you put it in water, dissociates to form sodium ions floating around with the water molecules and hydroxide ions floating around with the water molecules, right? And so, right, if we do our, right, if we look at the initial condition, right, we have solid sodium hydroxide, but it is, we know that we have, right? 4.0 times 10 to the minus 5 moles of that per liter. We got none of that and none of that. Our change, since it is a complete process, is going to be that all of it dissociates. So when we reach our final, right, our final point is not at equilibrium. We have no sodium hydroxide left. We have 4.0 times 10 to the minus 5 moles of sodium ions per liter, and, right, 4.0 times 10 to the minus 5 moles of hydroxide ions per liter. And so then we can consider our equilibrium, right? Sort of running out of space here, right? But our equilibrium is our Kw, right? Water, liquid, dissociating to form hydrogen ions and hydroxide ions, right? If we look at our initial there, right? It's a liquid, don't care, right? No hydrogen ions have been produced, but we have the 4.0 times 10 to the minus 5 moles per liter of hydroxide ions that we produced from our complete process, right? So our change is going to be minus x plus x plus x, and when we reach equilibrium, we'll still have liquid water, but we'll have x of this, and 4.0 times 10 to the minus 5 plus x of this. I think we figured out in the last one that that x is going to be really small, so we don't really need to pay attention to it there, and so we can solve for x the other way. Right, so here is our ending point from the last slide, right? So, right, we started with our, right, we still had our 4.0 times 10 to the minus 5 molar hydroxide ion from our original dissociation. That affected our initial concentration, right? And so if we solve for this, right, our Kw is 1.0 times 10 to the minus 14th, right? That's going to be equal to the hydrogen ion concentration, which is going to be x. Our hydroxide ion concentration is 4.0 times 10 to the minus 5, right? And so if we solve this, right, 1.0 times 10 to the minus 14 divided by 4.0 times 10 to the minus 5 equals 0.25 times 10 to the minus 9, which is equal to 2.5 times 10 to the minus 10. So that means the concentration of hydrogen ions that are in equilibrium with these hydroxide ions that we got from the dissociation of our base is equal to 2.5 times 10 to the minus 10 molar. So if you know the hydrogen ion concentration of a solution, you can always find the hydroxide ion concentration. If you know the hydroxide ion concentration, you can always find the hydrogen ion concentration using the Kw, right? Those are always linked.